Well, here I am for another physics program, and I'm beginning it today by having a cup of coffee outside Musk Restaurant in Clock Square. I think about electricity, which is going to be the topic of this program. I've got here a Bhutanese coin, 1 nultrum. There's one side to the coin and there's the other side to the coin. You can't have a coin which only has one side. And it's the same with development. Developments bring good and developments bring bad. The good and the dangerous. Let's take electricity. It brings us so many benefits. But also, and this is what I'm going to talk about in this program, it brings dangers too. Electricity brings us many benefits, but if used carelessly, if misused, electricity can be very, very dangerous indeed. It can kill you, it can maim you, it can burn you so that you're disfigured for life. So I want to talk a little bit today about the dangers of electricity and how to use it safely. When I use electricity, when I plug in my electric heater, I need to think carefully about how is the electricity installed, what wires am I using? Otherwise, I could have big problems. So in a minute, I'll talk a bit more about some of the problems that electricity can cause us. I'm looking in shops here for an electric iron and a toaster and perhaps a light. But it's really important if you go to a shop to buy electrical goods that the goods that you buy are good quality and safe, because if you get the wrong ones, they can be very dangerous. Let's see what they've got here at Sunempalden Enterprise. Well, I can see here in the window they've got some nice looking electric irons. So you hang on while I go and investigate electric irons. Well, I'm very interested in looking at your irons, and I see you've got some nice irons here, but what interests me most of all is whether they are electrically safe. Yeah. Because things which are not properly made can kill me. If I look at this iron, I see that, first of all, this is a steam iron. And if it's a steam iron, it means I put water in it. And as we've seen, water and electricity together are dangerous. So, doesn't this make the iron dangerous? The answer is yes, it does if it's not properly made. And you'll notice that this iron is properly made. First of all, that most of the body of the iron is plastic, which is an insulator, but the plate of the iron is made of metal, and metal conducts electricity. So how do I make sure this iron is going to be safe? And the answer is it's got 3 pins here. The third pin there is attached to the metal of the iron. And if one of the 2 wires that carries the electricity touches the metal, then instead of the electricity going through me and killing me, the electricity from the metal goes out through this 3rd pin here and down through the plug into the mains. The 3rd pin, the large one, is called the earth pin, and it's really important for safety, especially where you have any device with metal there. And when you get metal and water and electricity, those 3 can cause big problems. So I'm pleased to say this iron is very safe. Can I just look around? Here's a very nice little electric oven. I can use it for toasting things. But notice, this is made of metal. I have got electricity and metal. And if one of the two electrical wires touches the metal casing can give me a very bad electrical shock, unless there is a third pin to earth the metal case. And when I look at that plug, I say to myself, oh dear, dangerous. Metal case, but only 2 pins, no earth. But then I look at the plug and I see here something metal. And this is the third pin. This is the earth pin. So fundamentally, this is perfectly safe, provided when I plug it in my kitchen, that I've got a plug with an arrangement to contact with the earth pin here. I shouldn't just plug it in to a 2-pin socket. That would be very dangerous. So it's important to notice what sort of plug you have got on an electrical apparatus. So if I do it correctly, this is perfectly safe and very nice, so I'll have that as well. Now, I'm interested in one of your lights here. Well now, I look at it and I think that's a very nice light, but I notice, first of all, it's only got 2 pins. Now, usually for a light, that isn't too much of a problem. The thing to notice with this, though, is that this is metal. And if the wires inside here got old and broke, and one of these wires touched the metal column here, then if I touch the metal column, the electricity will come through me down to earth, and I will get a very bad electric shock. So it would be very important to be careful with something like this, to make sure that the wires and the insulation remain in good condition, and don't put it anywhere near water. So 2 pins, take care. 3 pins, much safer. So there we are. I've bought myself 3 pieces of electrical apparatus, 2 of them very safe, they have 3 pins. 1 I just have to take a bit more care with. Thank you very much indeed. Made of metal, a metal kettle. I connect it to the electricity. Now let's say in the beginning it's just got 2 wires. One goes into one socket of the plug, and the other goes into the other socket of the plug. Current comes down here through the heating element of the kettle, and then out and back up there. You'll want to tell me, of course, that with alternating current, it's going backwards and forwards like this, but fundamentally, current comes down one wire and back the other and back into the plug. Now, that's absolutely fine. No problem, until a bit of insulation here gets worn out and this wire touches the metal of the kettle. Then what happens? I come along here, that's me. I come along here and I pick up the metal kettle. I touch the metal. The metal now is connected to this electrical wire, and so electricity now comes from the metal kettle through me, through my heart, and down into the ground, thus electrocuting me, and I drop dead. Because a little bit of insulation there was worn out. So what can I do to make this metal kettle safer? Well, what I can do is have a third wire. And I'll draw it in blue, if I can find the blue pen. That's red, that's blue. If I now take a third wire from here and connect it to the body of the kettle, I connect it to the metal kettle, and here this big hole in the socket leads down to earth, then if the insulation here breaks down and this wire gets connected to the body of the kettle, instead of current coming through me, the current will come up the body of the kettle through the metal of the kettle, and it will come down the third wire, disappear to earth, the fuse in the plug will blow, cutting off the electricity supply, and so if I now touch the kettle, I don't get a shock. The function of the third hole in an electric socket and the function of the third pin on an electrical plug is to be connected to the earth, so that if one of the two electrical wires touches the metal body of the appliance, instead of current coming through me, electrical current will go through the large earth pin down to earth, cause the fuse to blow, and the metal kettle will be safe. People connect these wires wrongly, and that can be very dangerous. You must make sure that the earth hole in the socket is correctly connected to the earth pin of the plug. You get it wrong, and what you're actually doing is connecting the metal body of the kettle to the electricity. You touch the electric kettle and you will get an electric shock. So you must make sure your 3-pin plug and your 3-pin socket are correctly wired. And you should learn about how to wire a 3-pin plug in school. If you do, and I hope you do, make sure in your home you teach your parents and your brothers and your sisters and your grandparents how to wire a 3-pin plug. You check that your sockets are correctly wired. You, the younger generation learning about electricity, have a big responsibility to teach your elders about what for them is very new, that is to say, electrical energy. You, going to school, learning all about it, have a duty to carry your knowledge into your home. So here's a slightly larger 3-pin plug, and you can see there the 3 coloured wires that are going into it. Green goes to the big plug at the top. That's called earth. Red goes to the plug on the left here that I'm pointing to with my thumb, and that's called live. And the black wire goes to the right-hand plug, which is called neutral. So we have live, earth, and neutral. Now, it's really important that these wires are connected to the correct plugs here. If you get them wrong and connect the live to the earth, then when you plug it in, you will have a short circuit and everything will blow. And it will mean that if you plug it in, your electrical device, the casing of it, is live and will give you an electric shock. So live, red, earth, green, neutral, black. Remember, red for danger. This is the really dangerous wire. And it's very important that at the end the wires connect into the right places on your electrical device. And as I said, in school you should learn how to wire a 3-pin plug. Sometimes in a house there's an electrical socket there and you see there's a heater, a kettle, an electric fire, a computer, all plugged into one socket. That can mean that too much current comes through the socket, which will cause the wire supplying it to catch fire.
The electricity injury causes a lot of electrical discharges, abnormalities to your body, and at the same time this causes abnormality even to your heart. And as our body is also electrically charged, the electricity has 2 or 3 components when we actually get electrocution. First is a direct current, direct impact, especially on the part of the body that's in direct contact. Secondly, this current actually passes through the deep tissue and even to the bone. And thirdly, the current actually passes through mostly charged part of the body, especially like heart. And the electrical burn, superficially you may see that there is not much of danger, but the current actually passes through the body and even through the bone, and this is one of the very dangerous type of burn. The other disfigurement that the electrical burn can cause is this actually burns the muscle deep inside, the bone, the nerves, and the blood vessel. And first and foremost, it's not only the current, it's also that the electrical burns can actually cause other traumas, because you are either, because of the electrical current, you may be thrown away from that site of the injury, and you may cause other injuries like head injury or break your bones. So I hope that the people or the general public will take care of preventing yourself and your children from getting direct contact to the electrical burn, and as far as possible to take safety measures, because electrical burns are one of the most disfiguring injuries that you can have. And sometimes you will, if you have simple electrical burn, and if you are having breathing problem or chest pain, I think you must rush to the hospital as soon as possible.
What have they done wrong? First of all, Chunku got an electric shock and it paralyzed his muscles and he couldn't leave go of the electric socket. And then this chappie came along, took hold of his hand, and as soon as he took hold of his hand, this chappie got an electric shock. And you notice I can kick him with my shoe because my shoe's got thick rubber on the bottom. If I kick him with my shoe, I don't get an electric shock. The mistake he made was to take hold of the little boy's hand, because he's now getting an electric shock through the little boy. What should he have done? Remember this. If you see somebody having an electric shock, don't touch their skin. If I touch him there, I will get an electric shock. What I do is to take hold of clothes, because clothes are an insulator, and pull him away. If I can't get hold of clothes, then I quickly find a piece of cloth, very quickly, and I use the cloth to pull him away like that. And then I use the cloth to pull this one away like that. You don't touch the skin. What we have to do is turn him over and then give him cardiac resuscitation. Remember, if somebody's getting an electrical shock, don't touch their body, use their clothes or a piece of cloth to pull them away.
The electricity injury causes a lot of electrical discharges, abnormalities to your body, and at the same time this causes abnormality even to your heart. As our body is also electrically charged, the electricity has 2 or 3 components when we actually get electrocution. First is a direct current, direct impact, especially on the part of the body that's in direct contact. Secondly, this current actually passes through the deep tissue and even to the bone. And thirdly, the current actually passes through mostly charged part of the body, especially like heart. And the electrical burn, superficially you may see that there is not much of danger, but the current actually passes through the body and even through the bone, and this is one of the very dangerous type of burn.
When it comes to what sort of injury you're going to suffer from electricity, how much damage to your body electricity is going to do, we have to think about 2 formulas that you learn in school. The first one tells us that power, electrical power, measured in watts, equals volts times amps. Power equals volts times amps. Watts equals volts times amps. The second formula, which is important, is the old Ohm's law formula. V equals I times R. Voltage equals current times resistance. Now, we can turn that formula around and say current equals voltage divided by resistance. Now, to be damaged by electricity, what really counts is the power that's going through your body, the energy per second that's being pushed through by the electric power. Power is volts times amps, and if you think about it, I could have a big volts but a very low current, and that would give me the same power as a low volts but a very big current. Big volts, small current is the same as small voltage, big current. Now, I don't know whether you've ever experienced getting out of a vehicle, a motor car, on a dry day, especially in winter. You slide out of your car, you touch the handle of the car door to close it, and what happens? You get an electric shock. The electric shock you're getting then when you slide out of your car is a few million volts. That's a very high voltage, but the current that goes through you is very, very tiny, perhaps 1,000th of an amp. So you feel the shock, but it doesn't really do you any damage, except giving you a shock. Sometimes a fairly low voltage can cause a big current, and we now think of current equals voltage over resistance. If I have 12 volts and a resistance of only 1 ohm, I will get 12 amps flowing through me. That would kill me without any doubt. But fortunately, the human body has a much higher resistance. In fact, it's quite funny. Our skin, a bit like leather, our skin is a very good insulator when it's dry. But if your skin is wet, it becomes a very good conductor. In other words, the resistance is small. So let's think about 220 volts mains. If my skin is dry, there'll be a high skin resistance. So if I accidentally touch the mains, the current might be fairly small. But if I touch the mains and my skin is wet, the resistance is much lower. I equals V over R, small resistance. I will get a big current, and that will cause me serious damage. So water and electricity do not mix. Let me show you how wet skin conducts better than dry skin. I've got here a meter which measures how well something conducts electricity. I'm going to turn it on to measure how much electricity is flowing through. If I touch these two together, you'll notice the needle goes right over to the right. The resistance is tiny, so I get a big current flowing. However, I wonder if you would come here and let me test the resistance of your skin. Let's try, where shall we try? What about here? Now, your skin is nice and dry. Let's see how much current flows. I'm going to hold these a set distance apart, that far apart. Watch the needle. Let's move your arm underneath the needle. Watch the needle. Tiny little movement, tiny little current flowing. Now let's try. Skin is a bit damp. Watch the needle. Now more current flows because the resistance of the wet skin is even bigger. So I think you're dry up here and you're wet there. So you can see very clearly wet skin conducts electricity much better than dry skin. And if I could ask you to stick your tongue out, with luck, your tongue is very wet. We need to be able to see the meter, and I reckon if I touch your tongue, the needle goes right over to the right because your tongue, being very wet, is a very good conductor. So remember, water and electricity do not mix. The combination of the two is very dangerous. In a kitchen or a bathroom where you have water and electrical appliances, you have to take extra care. Talking about how well something conducts electricity, we have to be really careful. Wet skin conducts electricity, but also so does wet wood. Dry wood is a fine insulator, but wet wood conducts electricity, so can be a bit dangerous. Now, here I've got a pencil, and I'm going to try to put electricity through the pencil. Some people will try to put out a fire by throwing a bucket of water on it. Well, if it's an electrical fire, you have to be very careful. Water can conduct electricity. You throw a bucket of water on the fire, and the electricity comes up the water and you get an electric shock. So with an electrical fire, you don't put water on it. Very dangerous. You have to either smother it with a blanket to stop the oxygen getting in, or use a fire extinguisher, which is designated on the label OK for electric fires. So if you work in an office or wherever that has fire extinguishers, always check what sort they are. My friend here is going to stand here ready with this fire extinguisher just in case my pencil explodes when I put electricity through it. And here is a very kind technician from BBS who's going to turn on the switch while I get well out of the way, and for safety he's going to put on safety goggles, because if the pencil exploded and bits of burning wood went in his eye, that would be dangerous. I hope it's not going to explode. But just watch. Will the pencil conduct electricity? Let the fire extinguisher man feel the pencil. Now, the reason why there was a big flash and then nothing more happened, it just got very hot, is that the fuse in the plug blew, cutting off the electricity because so much current flowed. But even in that fraction of a second, the pencil got very hot. Had the fuse not blown and I'd allowed current to pass through, then the pencil would have caught fire. Why? Not because electricity is going through the wood, but because electricity is going through the pencil lead, which isn't made of lead at all. It's made of carbon or graphite. So the electricity goes through the graphite in the pencil, and this will cause the whole of the pencil catch fire. It's a bit like what happens in the electric chair, Because if you're put in the electric chair, which is what happens in America, very uncivilized, current passes through the spinal cord and your spine boils, just like this pencil would have caught fire because of electricity going through the graphite. So electricity can cause fires very quickly. And as you heard Dr. Tashi saying earlier, electricity, if it goes through your heart, disturbs the little electrical pulses which make the heart keep on beating at the right speed. And 30 thousandths of an amp, a very small current, if it goes through your heart, can disturb the heart rhythm and cause you to die. It's called defibrillation. So burns, disturbances to the heart, those are two of the major dangers. And how much current goes through you, how many amps goes through you, depends on the voltage and the resistance of your body. Water reduces the resistance of your skin, so electricity can get into the organs more easily. Water and electricity together are a dangerous cocktail. In bathrooms and kitchens, you must check that your electrical installations and that your electrical appliances are safe. You need to understand electricity. You need to understand your two school formulas, volts times amps equals watts, and current equals voltage divided by resistance. You need to know what affects the resistance of the human body. You need to check things like insulation around wires is not damaged. You need to check that the wires you use are thick enough to carry the current that your device is going to take. For example, an electrical heater takes more current than an electric light bulb, and so you need thicker wires to connect an electrical heater than to connect a light bulb. The size of the electrical wire is important, and if you get the wrong size, you can set fire to the insulation, which then sets fire to the building. And it's very possible that the sad loss of Wangdi Phodrang Dzong was, in fact, the result of an electrical fire. So electrical safety is very, very important.